Oh, yes. Yes, yes, yes. My AV guy is giving you the evil eye.
What happens if you move it enough?
He gets mad. We're good. Okay. Great. So welcome to the final lecture of the DARPA Sheaf tutorial, the tutorial on data analytics and sheaves. We're going to talk now a little bit about noisy data. And primarily, this is an entree into some persistent homology and cohomology, as well as a few other ideas that come around for dealing with distortions and robustness and such things. So where are we? We're at the very end now. So we've talked about topology. We've talked about sheaves built on topological spaces. We've talked about various kinds of homological tools for extracting information from linear algebra, and then mapping our topological machinery into linear algebra to talk about homology of topological spaces, as well as sheaf cohomology. We'll talk a bit more about such things now to finish this up. Now, I will say this is not the end of the story. There's a lot to be learned and a lot to be thought of now. So what we're going to talk about first is we're going to talk a little bit about pseudo-sections, which are a somewhat flexible version of what a section is, allowing you to manage some kind of error tolerance. And then we'll talk about persistent homology, which is persistent homology is a particular kind of sheaf. And we'll talk about how we can use that to find some useful features. We've mentioned this computationally a few times, and we'll actually delve into what's actually happening under the hood. Okay, great. So one of the problems that you might have, and we mentioned this before already, is that if I have two data sources that are telling me something about the same kind of phenomenon, that you might not get exact matches. Now, what I had suggested that you do if you're dealing with images, is I gave kind of a recipe that might work, is to go to the detection level, to fuse at the level of detections. Now, what if, in fact, you want to deal with more approximate matches? So not quite this severe situation, but rather a situation that's much more common when you're mosaicing images, where there's a certain level of distortion you're going to tolerate. So the matches are not perfect, but not too bad. In essence, what we want to do is we want to look at the same ideas that we were thinking about with cohomology, where data coming in from the two vertices into an edge, or from the low-dimensional faces into a higher-dimensional coface, when I take the difference of that, that's what I'm doing when I'm computing the coboundary. When I compute that coboundary map and the difference is small in some sense, then maybe I'm willing to accept that. So what do I do? Well, here's an example. And this is a heterogeneous kind of example. Starts out as a homogeneous one, and I'll make it heterogeneous. So I could be measuring the temperature of a particular object, and if I have two independent measurements of it that each say the object is 200 degrees Fahrenheit, so this is one data source says 200 degrees Fahrenheit, the other one says 200 degrees Fahrenheit, and the object itself really is 200 degrees Fahrenheit, then yeah, everything is equal, everything is consistent, got identity maps there, all equal, it's a section. Okay, now the problem is, and this is one of the sort of problems with sheaves as typically written, is that if I tweak something, say this measurement says 199 degrees Fahrenheit, which maybe is pretty close to 200. Maybe this is some delicate chemical process, but generally speaking, if we've got 199, it's pretty close to 200, and maybe the actual thing is 201. Strictly speaking, this is not a section. They're not equal. That's not so good. Maybe instead what I'd like to do then is I'd like to actually check the variance of these pieces of data. So if I take the variance of these various pieces of information that are coming together at this particular spot, and that variance is small enough, maybe less than 10%, then I'll call it a pseudo-section. Not quite a section, but a pseudo-section. Saying that I'm going to accept that error tolerance, and I'll consider those measurements to be self-consistent. Now, you can do neat things with this that are a little bit bizarre. If instead of using variance, I use some other function that takes in these three values and returns me a truth value. True if consistent, false if not. So for instance, I might have this sort of situation where the thermometer on the object says 50 degrees Fahrenheit, but there's a big label that says burn hazard. Maybe I don't want to touch that. Because even though these pieces of information don't necessarily look consistent, maybe the truth value here is saying that, well, maybe I should probably avoid this. So this idea of relaxing very heavily the notion of what I mean by consistent to just being some random function maybe is the right idea. So that I pull together from all the various cophases and then make a determination about whether it's consistent, more or less independently of the algebraic structure. Well, maybe that's a good way to do things. So if you do that, this is a fairly technical way to say this, but graphically what we want to do is sitting down at each non-vertex simplex. So sitting down on an edge and asking what data do I need to check for consistency at that edge? Well, at that edge, I need to check for consistency the data coming in from the vertex on the left and the data coming in from the vertex on the right. And I may also additionally have some data already at that edge. So those are 3 pieces of information. Now, if I have a 2 simplex, I have data coming in from each of the various edges, as well as data that might be already present there. So that's 3 edges plus an additional piece of information. The 2 simplex then has how many pieces of information? Has an additional, let's see, I see 1, 2, 3, 4 pieces of information on that 2 simplex. So it seems like I need about 2 more than the dimension of the simplex pieces of information. And what I should do is I should walk over each of the various faces and aggregate that information. This particular model here assumes that all the stalks are the same, which is a little bit of cheating. But essentially what we want to do is we want to gather up all of those pieces of information and say, I've got at that simplex, I've got a function. That function is going to check consistency, give me a true or false value. True if consistent, false if not. So what I can do then is build up a model that says walk over each and every non-vertex simplex, check all the data for consistency. If true, then I'm going to say it's a pseudosection there. And if I have pseudosection over everything, then it's a global pseudosection. So same idea as sections and local sections. So this is kind of nice in the sense that it captures the problem because it gives you a lot of flexibility about what you mean by consistency. The disadvantage is, that, gosh, how the heck do I compute this sort of thing? How do I even deal with this? I mean, this is completely separate from the framework that we've been working with for computing cohomology. There's no linear structure here. These functions can be pretty much arbitrary. What do I do? Well, it turns out, and this is somewhat of a hack, but it turns out to be theoretically true, that actually pseudosections are actual sections, bona fide sections, just of a different sheaf. A sheaf over a very different complex. So if I started out with this simplicial complex, put a sheaf over it, and then added these functions to each non-vertex simplex, so that edge, that edge, that edge, and this simplex, to check for consistency on each of those spots, really what I should be thinking of, if I want to think of this as a sheaf, I could encode those consistency checking functions into a sheaf over this barycentric subdivision, because now what I'm going to do is I'm making the stalks at each of these vertices capture the consistency requirements there by specifying only the consistent data at each of these points. And then I end up with a bunch of projection maps as restriction maps out of these things. So it turns out that even though this seems way more general, it actually isn't. And that's, in some sense, corroborating the fact that I said from the beginning, sheaves are the canonical way to do this. So I shouldn't have to actually add any additional machinery to keep the same theoretical power. Now, there may be some practical reasons why you want to compute with pseudosections and specific consistency functions. That may be easier intellectually to think of these as separate information sources, because now I have to discriminate between information sources and consistency test sources, so to speak. They're kind of like sources, but kind of not. Take that as you may. At least theoretically, it suffices to work with sheaves. So this is kind of nice in the sense that what sheaves already have the ability to manage noisy data in that fashion. Yes?
There's no demand for recurrence? You're getting the fractal...
You only have to do it once.
One
One round of barycentric subdivision is sufficient. Okay. We're not having to recurse and go all the way down.
I'm just a little confused, because if you look at this barycentric thing, I mean, you're having to do comparisons of lots of different things. I mean,
Yes.
there are 6 different nodes there, whereas here are only 3. So So what are all these extra comparisons?
Good question. Okay, so what we're doing, so let's actually suggest what are we doing here. What we're doing is we're asking for comparison between data, say, at this vertex and this vertex. How do I compare the data between those vertices? I map them into this edge. Well, I'm asking for consistency at this edge. So how do I measure consistency at this edge? Well, I take data from here and data from here. So in fact, that consistency test is at this new vertex. This new vertex is testing for consistency between these two guys. Then similarly, if I'm testing for consistency between these three faces, well, that consistency test happens sort of at this simplex. Hence, it's going to happen at that consistency checking vertex. And that's why only one barycentric subdivision is necessary.
So the center one is the three-way?
The center one is, in fact, the three-way. That's right. So in essence, the point is that really sheaves do suffice for managing even noisy data. So that's something that's theoretically nice. And in some sense, I don't have code that computes this yet. I don't have code that works on this, in part because, well, it suffices to work with sheaves. And furthermore, my code's not very optimized anyway. So I'll leave that there and move on to persistence, which those of you who are here finally obviously have some persistence.
Yeah.
So let's talk about what that is. So let me give you two examples that are sort of notional and get the ideas of what persistence is about. Persistence as a concept, and we'll drive into persistence specifically to homology. So the top sequence of maps, if you look at the labels that are present in that top sequence of maps, well, I see a bunch of labels. Very farthest zoom out, I see some country names and some state names. So I start zooming in, I still see some state names, although the country name went away, and some of the city names start to show up. And I zoom in more and more, I get more and more city names. If I look also at this zoom level here, I don't see any roads, but here I start seeing some interstates. Keep seeing interstates all the way through, and eventually pick up more and more local roads. So this is a map of sequence of maps of increasing detail. Now, if you say, mark out, all right, I see some state names, and they're valid all along here. I see some city names, for instance, Washington, D.C., shows up here. It's kind of hard to see, but it's right there. And it's there, and it's there, and it's there. So Washington, D.C. is something that's present for this 4 sequence of maps. It's not present there. And McLean, Virginia, shows up over here, and it's kind of in the bottom corner there. And as I said, some of the interstates, they show up here, and they persist through as well. So if you look at the longest places where I've drawn out a bar saying I've seen it in each of these images, and furthermore, I'm pretty sure this Washington, D.C. is the same as that one, is the same as that one, is the same as that one. That's why I can link this Washington, D.C.'s occurrence here to the Washington, D.C.'s occurrence there, etc. So if I do that and look for the largest bars, the ones that are the longest, it gives me an idea of what it is that I'm looking at in this sequence. It's not 100% conclusive, and in particular, it might not say very much at this level here, but basically this is a sequence of maps that mostly talks about Washington, D.C. and its surrounding areas, including the focus on the interstates, which indeed it is. So it's some kind of notion of scale. Now, on the other hand, this is a sequence of maps that are all the same spatial scale, but it's through time. And if you didn't know this about Washington, D.C., we recently were noted as the worst city in the country for traffic. So this is some historical traffic from Google. And if you look at when you see lots of traffic on which roads, it tends to cluster at a particular time and another particular time. These are throughout the course of the day. And of course, this is rush hour. So instead of seeing persistence through space, we're seeing persistence through time. And so you can draw the inference, perhaps, that rush hour is indeed a thing. Of course, if you drive around in Washington, D.C., you will know rush hour is a thing. So persistence really is about measuring the things or the objects or the ideas or the concepts that are valid from throughout a particular data set for a lot of pieces of the data set. And the other important point is you need to be able to match up one particular such instance of, say, a city name with that same city name as you pass all the way through. So the point is, if I can tell that there's not only it's something that shows up for a lot of the data set, it persists over a large swath of data, but also that it really is the same thing, that I can watch its identity and track its identity through this data set for a long period of scale or time or whatever, then in fact I'm really looking at the same thing. Okay, so persistence. So actually I misspoke a little while ago. Persistent homology is a co-sheaf. Persistent homology is a co-sheaf. Persistent cohomology of sheaves is itself a sheaf. And so this is something that you can kind of look at. Suppose I've got a bunch of sheaves and a bunch of sheaf morphisms. So I've got just a big, long sequence of sheaves, one mapping into the next, mapping into the next, mapping into the next. You could think of this as being a sequence of models, of data collection systems or some sensor systems of increasing fidelity. As I go from one model to the next, I get more and more data, more and more information about that data. So perhaps a multi-scale or multi-resolution model. Now, we did say cohomology is a functor. So cohomology being a functor means that each one of these sheaf morphisms turns into a linear map. Linear map from one to the next. So if there are a sequence of linear maps, I can ask the question, what happens to the elements of these linear maps? And in particular, what happens to particular bases of these vector spaces as they pass through this sequence of linear maps? I will immediately caution you that this is neither an exact sequence nor a chain complex. This is just a sequence of linear maps. No further properties necessarily at this point. But now I can ask, what happens to a particular basis element as I follow it through? Well, what could happen is I could have a particular basis element that shows up, that's present here, and when I map it forward, it's non-trivial here. So I've got a non-trivial basis element, still a basis element here, but when I map it through here, it ends up being the kernel of this map. So it maps to 0. On the other hand, I could have the opposite thing happen. I've got a particular basis element that shows up here and is not in the kernel here, is not in the kernel here, but never is not in the image of this map. It's not in the image of this map, so it really is something new. So this allows me to end and start some bars diagrammatically. And this is how you build a barcode diagram. So you walk through a sequence of vector spaces, and you ask when do certain basis elements either suddenly become mapped to 0 or lie outside the image of the previous map. This is, in fact, what persistence is about. And the question is whether or not I can decompose my space decompose my whole sequence of vectors into a sequence of linked basis vectors. One basis vector being such that it persists through for some period of time. Is there a canonical decomposition of this sequence of vector spaces into these self-consistent basis elements that persist across the whole thing? If so, then that's a good thing. Turns out, theorem, that you can do this, assuming a bunch of things. One is that you've actually got this sort of linear ordering, linear sequence of vector spaces. And the other thing is that you're using the appropriate field. Assuming that these things are really vector spaces, et cetera, this works out OK. That goes under the name of Gabriel's theorem. So this construction, although I've shown it for sheaf cohomology, it works for homology, works for co-sheaf homology, works for sheaf cohomology, and all these various other permutations of these words. You just have to make sure that you actually write down the maps appropriately. And the fact that you've got this construction like this is basically all that matters. Now, it's important that you've got this sort of linear ordering. In fact, if you know what a Dynkin diagram is, it works whenever your diagram is a Dynkin diagram. And in that context, you can write down a canonical decomposition of basis elements that are consistent across the whole lot. So I've got a basis that is present at this vector space that maps into at least part of a basis over here that maps into a part of a basis over here, et cetera. And that's a canonical decomposition, as in that there's only really one way to do that. So The Deacon diagram thing's been known for a long time. Turns out recently there's been some additional items added to the list of other constructions that work. And I have to admit, it's quite a heroic paper. It is long, it is complicated, it is scary, but it works. So what you can end up with is you can end up then with persistent homology of many different constructions. It's worth noting in the literature, if the arrows do not all go the same way, I've got them all going the same way, it doesn't actually change the result, but it's called a zigzag at that point. And if you hear about zigzag persistence, that is making use of the fact that the arrows are not going all the same way. So, useful search term there. Okay, so let me talk about how this sort of thing works from the standpoint of homology. And this is usually done through the point of view of point clouds, usually using Vietoris-Ribbs complexes. And so it's kind of handy in that regard to think about this physically. So what you tend to do is take a sequence of spaces, in fact, take a filtration of spaces. So I have one space that's a subset of the next, subset of the next, subset of the next. And think of these things not just as being topological spaces. They certainly work as topological spaces. But if you think about them as being metric space, pseudometric spaces, so they have a distance on them. So I have a distance on the first one, a distance on the second one, a distance on the third, distance on the fourth, and the distances are all compatible. Which is to say that if I measure distance between 2 points over here, and then I measure the distance between those same 2 points over here, I get the same distance. So the distance metrics are preserved in some reasonable fashion. Essentially what I'm doing is I'm adding more points as I go. Now, you can ask, then what can I do with this set of finite pseudometric spaces? These are point clouds in some high-dimensional space is the best way to think of them. The tactic is to use what's called a Vietoris-Ribbs complex, which is basically a geometric object which is built up as an abstract simplicial complex where I take every simplex, and every simplex corresponds to a set of points with diameter epsilon or less. So we've seen pictures of these before, but if I've got something like this, if I form a Vietoris-Ribbs complex with diameter epsilon, I get a certain construction. So I get something that looks like these guys here within epsilon, these are within epsilon, those are within epsilon, like that. And you fill it out so that it's the flag complex. So that's diameter epsilon. If I make maybe epsilon prime a bit bigger, and look for diameter epsilon prime, I end up filling in this here with a 3 simplex, and let's see here, I guess. This is kind of just outside, but this one's inside, so I guess I filled this in with a 2 simplex, and maybe I can't really, I guess that's just outside. So you can end up with a variety of spaces, and as you make the epsilon bigger, your spaces get bigger. The spaces include more and more simplices. Same number of vertices, but the simplices get more and more prevalent. So this gives you an inclusion, one Vietoris-Ribbs complex into the next. The benefit of that is that these inclusions of one Vietoris-Ribbs complex into the next, I can write a map from this Vietoris-Ribbs complex into that one by merely taking each simplex here and interpreting it as being over there. That's a map, and then homology is a functor. So you get the following kind of picture. So I start out with a bunch of points with a small threshold. This dimension here is threshold. I'm saying signal level, but you could think of it as a threshold or a distance, that epsilon. And as epsilon increases, the balls start to get a little bigger and bigger. And what's happened between here and here is I've gone from 1, 2, 3, 4 connected components, dimension 0 homology elements, no dimension 1 because there's no loops. And right at this particular critical point, well, those 2 connected components have merged together. Now, I don't actually, from this diagram, know which 2 merge together. I know this one here is no longer present. It's gotten mapped to 0. But remember, these are bases. Bases of vector spaces, so they're not necessarily unique. So it could have a little bit of ambiguity about, well, did this one stick on to this particular basis element or this particular one? I don't know. So I don't exactly know which one merged, and it turns out to not usually matter very much because of the fact that I've got this canonical decomposition. Okay, but if I expand the size a little bit more, well, more sticks together. I've only got, finally, these two merged together, and then finally this thing merged down to one connected component, and right when that happened, I formed a loop. So this loop shows up. Now, if I expand the size a little bit more, that loop goes away, and I'm left with just one connected component from there on out. Now, you can measure these sort of things in actual practice. So let me show you a laboratory experiment for measuring these. We've seen these kind of computations in the interactive session by measuring some of the wireless access point data. But here's an actual systematic laboratory experiment that I conducted. So here's a small acoustic transmitter. It makes, well, can't really describe it besides saying it's an annoying noise. It's some kind of digitally chirpy noise. That digitally chirpy noise that it makes is received by a laptop computer's microphone, listens to that digitally chirpy noise, and each of these, I built several of these transmitters. They each have a coded waveform, so the laptop receives the coded waveforms from each of them, so it can uniquely identify them and say, that's transmitter N that I'm hearing. It's accurate to about half a dB. Collected this over a period of about 45 minutes in this following region, portion of my laboratory, otherwise known as my living room.
What did your wife say?
I did. Very good question, actually. I did this while my wife and kids were out. It took a swath of 45 minutes to collect this data. I put on earmuffs so I would not go nuts. But in any event, I've got the receiver there and a variety of transmitters. Looks like my circles are a little offset. There's one of the transmitters there. There's another one there. And swept this receiver through the whole domain, and in some cases had an obstacle here, and in some cases didn't. So very much like the wireless access point data, where I have a variety of signals that I'm hearing at every given point, here I've got 4 different signals for 4 different transmitters that I'm hearing. And these are the signal levels as a function of position. These are reading out, I believe, in I think each block here is about 4 inches, so the axes are block numbers. I don't remember exactly the size dimension, but it's not that important. But you can see, for instance, that here on this particular transmitter's channel, you can see that the signal level drops off as you move away from the transmitter. Similarly, when this transmitter is transmitting, the signal level rolls off, etc. You can see the signal levels are not all the same. The transmitters do not all have the same transmit power. This is really organ basement equipment, so you get what you get. This is where I don't have any obstacle present in the scene. When I do have an obstacle present in the scene, well, I can't put the receiver there, so that sort of blocks things out. What ended up happening, though, is where that obstacle is present, you can see there's a little bit of diffraction around the object, so I get a little bit of signal level wrapping around it, get a little bit of a shadow region behind it. This particular signal level here is way off, way stronger than the rest because I swapped out the battery because that battery died. It doesn't matter. And so the question is, can I see this in the persistent homology of my data? Can I see the fact that there is or is not an obstacle? Now, to make this a little bit more fair, this has got fewer points than this does. So what I did is I randomly sampled both of these things down so that they're the same number of data points. So I grabbed a random number of points out of both of these and asked, can I see the fact that there's an obstacle, i.e. a whole topological feature, in this data set that there isn't in this data set? And if you go ahead and compute the persistent homology, so these are the list of dimension 0 generators and dimension 1 generators, dimension 0 generators and dimension 1 generators, or basis elements, versus when the obstacle is present versus when it's not. So these are the same number of points randomly subsampled from those domains. And I looked in particular when that when that remaining connected component shows up and all the rest are done. So all the data is merged into a blob. Are there or are there not loops? That's really what we're after. And if you look here when there's no obstacle present, you can see there are, in fact, no loops. That's because the domain that we're moving through is completely connected and contractible. Where here, when the obstacle is present, there is a hole. That obstacle is penetrating the domain, puncturing the domain. And so it's in fact present. Now, there's actually 2 generators of persistent homology, I suspect because actually we've got some diffraction effects that are causing that second one. So this says that, in fact, the obstacle is detectable using persistent homology. And so, in fact, what you should interpret this bar, perhaps, or maybe this one, it's unclear exactly, is this is actually a set of simplices that travel around and orbit around the obstacle. So not only are you saying that there is an obstacle, you're actually localizing it. There's actually some work by some folks at Penn, Ali Jadbabai's group, that has gone a little bit further than this. This data set's a little old, and said, well, actually, can I take this kind of data and then find the best such generator that loops perfectly around the obstacle, fits very tightly around the obstacle, so I can get a very good localization. And using some methods from Hodge theory, he's able to do that. It's a very neat thing. Now, you can do this for other sorts of things. This is the data set one of the data sets that I've given you, which is the ceiling fan sonar data set, where what I have is I have my handy-dandy cell phone that is transmitting a bunch of clicks, one after the other, very rapidly, at about 30 clicks every second, and then is listening to the echoes as it transmits. The realization was, this is not rocket science, but the realization is, if I have a cell phone, it can transmit and receive at the same time, because that's what a telephone does. Telephone transmits and receives sound at the same time, so if that's the case, my cell phone should be able to be pressed into service to do that. And I really was interested in, can I hear the changes in Doppler as this ceiling fan rotates? So as that ceiling fan rotates, the echoes that I'm hearing are a little different. Now, if you do this from the point of view of the ceiling fan is the only thing in the environment. It's sort of disembodied ceiling fans. I guess a fan, but no ceiling part. If I've got that disembodied fan, and I've got this particular phone transmitting and receiving, one thing that I will not be able to do is I will not be able to tell which direction the fan is spinning. Why not? Well, because there's a symmetry. If you take the line of symmetry from the phone to the fan, well, it looks very much the same when it's spinning this direction as it's spinning this way, because I don't have I have a left-right symmetry. Can't tell the difference between left and right. So if this side is going away from me and this side is approaching me, or it's the other way around, it looks basically the same. So I can't tell. But if you're not actually just disembodied fan, you're in the room, you're hearing echoes off of the walls as well, that breaks the symmetry. You're actually able to tell the direction of the fan's rotation, and you're able to detect that the fan is rotating. So I went ahead and collected this data. Here's what the data looks like. The vertical axis is range, so distance from the phone. Up at the top is 0 range, going down is increasing range. So there's a little bit of clutter near in. There, that smudge is the fan. And then this axis here, the horizontal axis, is Doppler, 0 Doppler in the middle. So the fan is in motion, so there's some Doppler spread. The fan is, on the other hand, not spinning at a constant speed. I just basically grabbed it and spun it by hand, so it is slowing down. That's why it's smeared in Doppler. It's not a single frequency. On the other hand, if you go ahead and you measure its persistent homology, say, give me the location of any persistent generators, as in of H1, which say, measure the loops that are present. Well, here they are. This is in a persistence diagram. So this is meant to be read as the birth versus death. So this is the start location, the start scale, the start epsilon versus the end epsilon. Do note, however, this says not persistent homology, it says persistent cohomology. This is work of Vin de Silva, and what his work was a realization that although he's not using sheaves, he's using the cohomology of a topological space that I mentioned briefly in the previous lecture. That translates to functions on simplices, and in particular, if you're looking at persistent first cohomology, it's basically like maps from the circle into your space. Well, that's kind of cool. That's talking about phase. Or is it perhaps maps the other way? It's not that material for this particular discussion. But basically what it's amounting to is it's assigning a phase function to your, it's maps, I got it wrong. It's maps from your space to the circle. So persistent cohomology is actually, first cohomology is isomorphic to the class of maps from your space to the circle, in essence assigning a phase. You can just then grab this particular cohomology class and examine what function does it result in. You can see there's angle as a function of time, so you can see the fan's rotation rate. Notice there's little wiggles in there. Those little wiggles are where we get some ambiguity as the fan hits certain points where we get some strange echoes coming off of corners. The multipath in the environment is showing up there as well. So this is a different persistent structure. So it's a persistent cohomology for finding functions as opposed to persistent homology for finding physical features and physical topological features in the data. So now is a good time to wrap up, and I'll wrap up all of our discussions thus far for this whole tutorial. So we talked quite a bit about what sheaves are. Sheaves are some kind of local to global fusion idea. And indeed, they're the canonical and right way to do things. And they are also, in some sense, the best case, where I can actually draw strong conclusions from fused data. If I can't draw strong conclusions from fused data, then I may or may not be able to get a sheaf. We talked a lot about how to encode a variety of data, heterogeneous data and homogeneous data, into sheaves, going under the lens and name of sheafification. And that talks a lot about how do I manipulate multiple kinds of data sets. We talked a lot about categorification and some of the implications of that. Then we took those sheaves that we found and constructed, and then analyzed them through the lens of looking at certain local and global sections, homological invariance, local homological invariance, and cohomology. And then we did a little bit of analysis of the sheaves in software. You've got lots more to play with that now as part of this tutorial. And I'm happy to field questions on any and all of these things. So please do ask. And finally, we've taken these and analyzed back into the context of the original data. So what's next? Well, there are many, many open questions that are in this field, and many that will be addressed in the upcoming DARPA Simplex program, as well as many that will not. The focus there is primarily on heterogeneity and hypothesis generation, but there are wide open areas that have not been touched on in the literature much at all. One thing is this notion of persistence for sheaf cohomology. It's something that seems very natural. I gave you the construction now, and it really hasn't been studied. We don't really know what you can learn from that. There's also this interesting duality between sheaves and co-sheaves, that being the duality between top-down and bottom-up models. It's been known for a little while that these things are related in some fashion. A recent thesis of Justin Curry from the University of Pennsylvania captured this and wrote down some important theorems, but there's a lot of work in trying to interpret that. There's a lot of work in understanding what they actually mean and the mechanics of and the algorithmics of manipulating them. And really addressing the aspect of large amounts of data using sheaf theoretic computations is something that really is only starting. We've got the various libraries that I've given you. There's a few other papers in the subject, but not much. There's a lot to be done there, especially with regards to playing around with new computing architectures, heterogeneous computing architectures, various kinds of sparsification methods. We really have a lot to learn there. So I want to conclude with sort of a philosophical viewpoint. That a lot of the best engineering and science problems are usually based on fun math problems, interesting math problems. And if you have a hard engineering problem that you can't crack, it almost always has got a neat math problem buried under there. So as an applied mathematician, and not just to this audience, but to the whole audience online that's listening as well, if you're interested in finding interesting math problems, a good place to look is in science and engineering, because there are a lot of hard problems there. And speaking as a mathematician, what we tend to think of is well, we are the center of the universe. We are the queen of the sciences, after all. Applications are merely corollaries of the great theorems that we all know and love. For instance, we know lots about differential equations. That, of course, has led to theoretical physics. We know lots about linear algebra. That's telling us all sorts of things about data processing. We know lots about dynamical systems. That led to control theory, right? And computational theory. Yes, we did that so that we could build computers, right? Well, no, not really. It really goes more like this. The interesting applications lead to better mathematics. Once we've got the better understanding of mathematics, then we can go back and maybe inform some of these things in a more useful fashion. Actually, I would say we can inform things in a more useful fashion. In fact, a good statistic that's often been quoted, it's quoted as a question, a rhetorical question. if you could have the computers of the 1950s and the algorithms of today, or the other way around, the algorithms of the 1950s and the computers of today, which would you prefer? Which would you prefer?
Depends on what you.
Clearly depends on what you're doing. Clearly depends on what you're doing. But in a surprising number of cases, having the better algorithms is more important. But that's, again, mathematicians' view on the world. So here's some further reading, and I thank you very much for your attention. And that is all.